And let's welcome the next speaker, Charles or Lawrence. Charles, yeah, thank you.
Okay, hi everyone, I'm Charles Margossian. I'm one of the co-authors on the Shrinkage Delinkage paper, along with Lawrence Saul. We're at the Flatiron Institute, which is a research institute in New York. We're part of the Simons Foundation, and we focus on computational methods applied to basic sciences, so physics, astronomy, biology. And for this particular paper, to set the stage, we're interested in variational inference, which is a class of algorithms to approximate a target distribution P using a tractable approximation. And the way we'll do this is we'll define a family of approximation Q, and within that family, we're going to find Z distribution that minimizes some measure of disagreement with our target distribution P. And what people usually do is they minimize the Kolber-Kleidler divergence from Q to P. And because Q is a rather simple family and the target P tends to be a complicated distribution, we're usually not able to make this measure of disagreement go to zero. So we solve the optimization problem, hopefully, and then our KL divergence is non-zero. So what? What is the price we pay from our approximation error? And that's kind of the theme of the research we're doing here. And in particular, we're going to focus on one particular family of approximations, which is the factorized or mean field approximation, where you just take all your variables to be independent. Now, this is done out of computational convenience. We don't actually think that the variables we're interested in are independent. They don't factorize. But nonetheless, you will find this somewhat crude approximation used in a lot of different areas, including statistical physics, Bayesian statistics, and some areas of machine learning. And again, I want to emphasize, we're doing this because of computational convenience. It really makes the computation faster. And the question is, can we get away with doing this kind of approximation? So the first elementary fact that I'll state is we're not able to estimate the correlation between the variables because we just set them to zero, right? Now, something that maybe is a bit less intuitive is because of this factorization approximation, we're actually not able to also get good approximation of the marginal variances, right? So this is common wisdom in the literature. There's a lot of papers that have been discussing this for 2 decades. And the phrase that comes back again and again is factorized variational inference tends to underestimate uncertainty. Okay, so how do we actually measure uncertainty? We had a whole session dedicated to the question. And I'm just going to point out 3 ways in which people have measured uncertainty in the literature. One is the marginal variance, which I think in Bayesian statistics tends to be the relevant metric. People also look at entropy, which in some sense is a multivariate generalization of the marginal variance, or they've looked at frequentist intervals. Right? I'm going to focus on the first 2 measures of uncertainty, and we're going to think about the relationship, but also the disconnect between the 2. So let's suppose that our target distribution is a Gaussian, and we're actually going to focus on a simple example because we're actually able to do the calculations analytically and still get counterintuitive results that will generalize to broader settings. And what I'm going to do is, as my approximation, I'm going to pick a Gaussian with a diagonal covariance. Right? This is actually very common when your latent variables are continuous. And so many people have examined this example, and this is the picture that comes back over and over again in textbooks and review papers. And what it shows is you have your target with some non-zero correlation, and then your approximation is a bit of a mismatch, right? You're able to match the expectation value, That's already pretty good. But you tend to underestimate the variances, and your approximation tends to be more compact, right? So you have this very common two-dimensional picture. And frankly, all we did was think about what happens if, we start going to higher dimensions, right? So we just went to dimension 64 because we like powers of 2. We're projecting on the first 2 coordinates, and you can see that just by increasing the dimension, it looks like you've made your approximation more compact. So less volume, suggests that you're underestimating entropy even more. You can see that you're underestimating the marginal variances in every direction. And then, of course, as I continue to increase the correlation, eventually my approximation becomes vanishingly small relative to my target distribution. And so let me give you right away the punchline of this presentation. If you look at the rightmost figure with the tiny, tiny dot, that's the approximation, it turns out that in this case, you are getting arbitrarily poor estimates of the marginal variances in every direction, but actually very, very accurate estimates of the entropies. And this two-dimensional projection is misleading. Actually, the tiny, tiny dot here has the same volume as the ellipsoid once you start building back into higher dimensions. So there you go. There's our counterintuitive result from studying this very simple example. And let me try and explain why actually we should expect this. And the first thing we're going to do is we're just going to prove some elementary results again, in the Gaussian case, which is, yes, you do underestimate the marginal variances. Yes, you do underestimate the entropy. But then we're going to think about what is the relationship between the entropy gap and the variance shrinkage. And this is going to lead us to understand why these two-dimensional projections that we see over and over again in textbooks and papers can be misleading. And then at the end, I'll talk a little bit about non-Gaussian targets. And the first thing is that because of this example, because I have this, I'm in this nice setting, I can actually solve the variational problem analytically. So you are able to match the means. This is what the first equation tells you. The second equation tells you this is your estimate of the marginal variances. And it's 1 over the ith diagonal component of the inverted matrix. So you actually match the diagonal elements of the precision matrix. You can think about it this way. But unless this covariance matrix is diagonal, you're not going to correctly estimate the marginal variances. And so, once you have these calculations, you can do some, clever manipulations to prove that you are underestimating the marginal variances in at least one direction, and you have an entropy gap. The proof of one is a few lines, but it's not very methodical and insightful, in my opinion. But the proof of the second term, which is the entropy gap, all you do is you write explicitly the entropy of the Gaussians, and you find that this entropy gap corresponds to the KL divergence at the optimal solution. And you know that that KL divergence has to be positive. So going back to my question of, okay, so what? The KL divergence is positive. Is that really a problem? Well, it means that you have a large entropy gap, right? If your KL divergence is positive. And maybe that's something that's a little bit more interpretable. And so now the question is, okay, does a strong variance shrinkage mean a strong entropy gap? Are the two related? Does entropy really generalize variance in a conceptually meaningful way? So I'm going to introduce two actors here. One is the correlation matrix of my target distribution, and the other one is this shrinkage matrix. It's a diagonal matrix, right? And basically, it's the ratio of the true marginal variance over the approximate marginal variance. And this is the shrinkage delinkage trade-off, which tells me that the entropy gap is going to be due to two competing forces. One is the log of S, and what this is saying is the more you underestimate the marginal variances in every direction, the more you're going to underestimate the entropy. So this is exactly what you expect. But then you have this other term that comes into place, and that's called the delinkage term. And what this is telling you is because you have a factorized approximation, you are forcing the correlation between your latent variables to be 0. And in doing that, you're actually increasing the entropy of your approximation, right? And so the reason we call this a delinkage is because if I think about my original graphical model, where I have a link between all my variables. In my approximation, I am breaking those links. And so now I can ask, well, how do these two forces compete? And what is the ultimate outcome? Well, we saw that eventually variance shrinkage wins, right? The entropy gap is always positive. And we can demonstrate that across a series of examples. So this is looking at one particular kind of Gaussian. This is a squared exponential kernel. But now I'm going to look at another kind of Gaussian where all the off-diagonal elements of the covariance are constant. It's my epsilon. And you can see that the delinkage term almost completely compensates the shrinkage term, right? And now again, I'm going to ask what happens if I start going to higher dimensions. Well, it looks like the gap becomes smaller and smaller and smaller. And you can formalize that. Let's suppose that we have this sigma with a constant off-diagonal term, and let's look at the limits where our dimension goes to infinity. We can show that the entropy gap per component vanishes. So you actually get accurate estimates of the entropy. And at the same time, you have arbitrarily bad estimates of the variance in every direction, not in just one direction, in every direction. So how do I reconcile these two pictures? This tiny dot here, that's my approximation, and this entropy gap that vanishes. And so what you need to do is just think, okay, this is a two-dimensional projection. It's misleading. What happens as I start projecting into higher dimensions? So think about your sphere, right? If you go to higher dimensions, it actually gains volume in every direction. Whereas the ellipsoid only, because of the strong correlation between all the variables, it's almost only going to live on a submanifold. And so you keep increasing the dimension and the sphere keeps getting bigger and bigger, whereas the ellipsoid doesn't really grow until at some point the sphere has the same volume, almost the same volume as the ellipsoid, right? And really what this is telling us is, look, when you're doing a factorized approximation, you're not going to be able to both match the marginal variance and the entropy. You can match one or the other. And it turns out the choice of objective function with which we're doing variational inference, which is minimizing the scale divergence, chooses entropy, right? Remember, we showed that the scale divergence at the optimal solution is the entropy gap. This is what you're going to focus on. And the only way you can make this entropy gap smaller is by underestimating the marginal variances in every direction, right? This is what's going on here. And so, of course, I think we tend to think about, okay, we have a variational approximation that fails. What if we had a different variational family that's richer, that's more expressive? Here, I want to invite you to think about what happens if you change the objective function, right? So very simple change. I'm going to take the KL divergence in the other direction from P to Q. And what is going to happen here, I'm actually going to get a very different behavior, which is that by minimizing this reverse scale divergence, I'm going to get exact matches of the marginal variances. But this has to mean that I'm not going to estimate the entropy correctly. In fact, I'm going to completely overestimate the entropy. And so you can see it on the two-dimensional projection. But obviously, as you start going into larger and larger dimensions, the sphere keeps growing. And so this has, a few implications. One, there's a methodological implication. We need to think about what objective function we're using with VI, but also it's an invitation to think about when can we get away for these approximations, depending on the application, right? So I look at statistical physics, where this mean field approximation comes from, right? And people were interested in estimating free energy. They're actually interested in the entropy itself. And they look at these Ising models. You can draw a connection between the Ising models and these Gaussians. And they show that in the infinite dimension limit, you get very accurate estimates of the entropy, right? This is a case where I can totally justify the mean field approximation. On the other hand, I look at Bayesian statistics, where oftentimes I'm going to be interested in quantifying uncertainty for interpretable parameters. I care much more about the marginal variances than I do about the entropy. And maybe you have other examples in mind, and I'd love to hear them where the entropy matters. I have rarely seen that be the case in Bayesian statistics. And then I get into machine learning. And so really what I have in mind here is, something like a variational autoencoder, where I'm going to, try and get an approximation of a marginal likelihood, right? That's where I'm throwing my variational approximation at it. And so we still kind of have to look at it, but my conjecture is that you have a lot of models where actually, even though you're doing a poor job approximating those decoders, which really approximate, some conditional distribution, you can still get good estimates of the marginal likelihoods with this mean field approximation, right? But this is a conjecture and it's going to depend on the cases, right? So question mark for the latter point. So with that, we've done all this analysis on the Gaussian case, which is on this, it's obviously it's a, I don't want to call it simple. Well, it's a simple case, but it's a profound case, I would say. And so now we can say, well, what happens when we get to non-Gaussian cases? And so this is a target distribution. It's cool. It's a standard hierarchical model where we look at the marginal variances. And what we found is that, for a Gaussian that has the same covariance as this target, our theoretical results hold. But you might actually have cases where you overestimate the marginal variance with the VI approximation. However, what we did find is that on average, you will underestimate the marginal variance. We showed that across a series of examples. There are a lot of biomedical examples here, actually. And then we also ask, okay, can we empirically study the entropy gap? And the problem is it's very difficult to estimate the entropy, even if you throw a lot of computation at it. The approximations that exist make a Gaussian assumption, which is exactly what we're trying to relax. What we do have is an upper bound. We can show that the upper bound is always positive. It would be more interesting to have a lower bound. But there's a very nice result by Turner and Sahini, where they were able to construct an example where VI overestimates entropy for a mixture of non-well separated Gaussians. Right? So with that, I just want to ask a few open questions. This shrinkage delinkage trade-off, we showed it explicitly on the Gaussian case, but the intuition that underlies it is not specific to the Gaussian target. It's not specific to the pure mean field approximation. It can also work with diagonal plus low rank approximations. We want to understand entropy a little bit better, and we want to think about other objective functions or pseudo-objective functions that people deploy in the literature. And so with that, I'll open the floor to questions, although I think I have the intervention of a discussant first, right? Okay, great.
Let's welcome Ryan for the discussion. Ryan.
Hello, can you hear me?
Yes.
Okay.
Hi, Ryan.
Hi. All right, so I think I have some, here we go. All right.
Yeah.
Okay, so I'm Ryan Giordano. I'm really grateful and happy to be the discussant for this just fantastic paper. I was really glad they asked me to do this. I'm at UC Berkeley. So first, I want to provide a little bit of high-level context why I think this paper is so great. We've known for a while that these restricted variational families, for example, this mean field family that Charles talked about, which models the posterior covariances as all zero, these can lead to poor posterior approximations. And so in response to this kind of now widely acknowledged fact, there are two very common responses. The first I might call the machine learning response, which is to ignore this problem. And you use your variational approximation, you plug it into your process, but you evaluate whether or not it's doing a good job according to some criteria other than the actual posterior. For example, you could model its predictive accuracy. This is basically something that like latent Dirichlet allocation does, for example, and that's great if that's what you're interested in. Another approach, which I would just call modern variational inference, is to use more expressive families. So for example, normalizing flows might fall in this category. But you remember we made this mean field assumption for computational reasons in the first place. And often when you make these more complex families, you get more accurate posterior approximations, but it comes at a computational cost that we're trying to avoid in the first place. This paper really tries to understand how this restricted family goes wrong, which is just amazing. I think that's really incredible. Now, I want to comment a little bit on their top-level conclusion, which, if you read it in plain English, is initially very surprising. And it basically goes like this. If you have a Gaussian case, you're trying to approximate a Gaussian with a Gaussian, but you're using the mean field approximation, and that target has a constant correlation matrix. Then as the dimension of that matrix goes to infinity, you get the marginal variances wrong by some non-vanishing amount, but you get this entropy correct, right? And the key word is this per component entropy gap goes to 0. Now that's initially crazy, right? It can't be possible that you actually get the marginal entropies correct and the marginal variances wrong. So what does this per component entropy gap actually mean? What it means is that when you normalize by n, the number of dimensions, the entropy gap goes to 0. Well, in fact, if you look at the paper, this entropy gap is order log n. So when you divide by n, sure, it goes to 0, but it actually diverges as n goes to infinity. So for this conclusion to be meaningful, you have to make a case that n is the right scaling, right? And maybe you could, but I would argue that it's not as clear, right? That n is the right scaling versus anything else. And in fact, in general, as Charles put very clearly, what we actually care about, at least when we're doing Bayesian inference, are these marginals, right? So I think I have one more line at the bottom of the slide. Could we hit next? Okay, right. So why is it that this entropy gap matters and its scaling does it matter as the number of dimensions go to infinity? I'd argue that when we're doing posterior inference, it's not very clear, right? And so I think Charles put it very well. This is an instance of this disconnect between what we actually care about when we do Bayesian inference, which is usually posterior marginal for a small number of dimensions, and what we're actually trying to optimize, which is this KL divergence, which again, we do for computational convenience, but which may not represent what we actually care about. With that, I commend the authors for this amazing paper. And Charles, if we have time, I would love to hear what you think about this comment.
Yeah, great. Thank you, Ryan. And I do want to say Ryan Giordano has done amazing work on variational inference and correcting for error in mean field approximations. So I can't highly enough recommend his papers on the subject. So with that, yeah, I think thanks for the detail. Yeah, it's order log n is what the entropy gap scales at. And the idea is the reason we rescale by n is because we have this idea that the entropy itself grows at roughly an order n scale. And so, like if you care about the error in your entropy gap, it's going to be the fractional error. So there's a way to present this result where we really focus on the fractional difference. Whereas if I were to look at something like the trace of the shrinkage matrix, which also scales with n, and I divide that by n, that's still not going to go to 0. But that said, this is something Lawrence and I went back and forth, and he was a stronger advocate of the scaling by 1 over n than I was, and I agree this is subject for discussion. With that said, I think we have time for questions.
Yeah. Any question from the audience? Yeah.
Yeah, thank you for the super nice presentation. Don't these results imply that perhaps KL divergence is not the right distance metric to minimize?
Absolutely. Well, again, I want to insist it depends on the application. I think we have Bayesian statistics in mind where we care about marginal variances. Again, you look at those applications in statistical physics, that's not what they care about. And I think that in ML, when we're trying to estimate those marginal likelihoods, it's not super clear what it is we care about. Again, it depends on the application. Now, what I will say in Bayesian statistics is I'd love to optimize the reverse scale divergence. I can't do that because I don't have a good Monte Carlo estimation or a scalable method to do that. But there are variational inference methods that use either objective functions or even pseudo-objective functions. I'll plug in some work we recently did at the Flatiron Institute, which is on Gaussian score matching, variational inference, where we use a different kind of optimization criterion. It's not an explicit objective function. And here I wonder, I'm not sure, how the shrinkage delinkage trade-off resolves when we're doing this kind of work. So, hopefully this is a blueprint for analyzing more objective functions. But yeah, and this was my big takeaway. We shouldn't only think about the variational family. Sorry, long answer.
Thank you.
Yes, I have a question here.
Yes.
Thank you for the very nice presentation. I really appreciate it. Actually, my question was about the result heavily depends on the Gaussian assumption, basically on the distributions. And the problems comes from the covariance, from the estimation of the covariance, basically in high dimension, as I understand. What is your thoughts about other distributions that have higher order moments? Can we still have this entropy gap in the estimation, that goes to zero, or how this is related to higher order moments, basically?
Yeah. The short answer is I'm not sure, and the long answer is longer. But I think that we want to think about how these results generalize in the directions in which they generalize. And it's true that the way you're able to get such a crisp write-out of these conceptual ideas is by focusing on the Gaussian case. And so now we want to ask, okay, what are some sensible generalizations to make, right? So we want to think about unimodal case, or maybe, because we know that in the multimodal case, funky things start happening. But even if there's the theoretical aspect of it, the theoretical analysis, but even studying these things empirically, it's not super clear how to do that. And I'm almost tempted to prioritize the empirical study, A, because I think it might be more accessible, but B, even if I work out the theory, I'll need to do that. And so I want to bit of a segue from the question you ask, but those are future directions I want to think about.
Okay,
and
thank you.
There's a poster this afternoon for more discussion.
Okay.
So I hope to see some of you there. Sorry.